Okay, here's a question. Let's say that we have a function and when we check it, we get one of our indeterminate forms and otherwise it meets the criteria of L'Hopital's rule, and so we apply L'Hopital's rule. But when we take the limit, instead of getting some constant value like we did in examples 1 and example 2, we get yet another indeterminate form. Well, provided that the numerator is differentiable and continuous on an interval containing a, and provided that the denominator meets those same criteria, we're free to apply L'Hopital's rule as many times as we need to. In other words, take the derivative of the derivative and take the derivative of the derivative on the bottom. So let's take a look at example number 3. Here we have the limit as x approaches negative infinity, x squared over e to the negative x. Now you might be tempted to rewrite this as x squared times e to the x, but that actually gives us a different indeterminate form. It gives us the indeterminate form infinity times infinity. And if you'll recall from earlier when we were looking at the indeterminate forms, I mentioned that one of the techniques for handling indeterminate forms other than 0 over 0 and plus or minus infinity over plus or minus infinity is to rewrite them in a clever way so that you get one of these two and can therefore use L'Hopital's rule. So it would not benefit us to rewrite this. Actually, this has already been set up for us to use L'Hopital's rule, so we're going to work with it like it is. Now let's think for a minute about what is going to happen here. If I substitute negative infinity for x, I get an infinity squared, which is just infinity. And if I substitute e to the negative infinity, that's e to the positive infinity. Well, that's just infinity. So we have infinity over infinity, an indeterminate form. X squared is continuous and differentiable on all real numbers. E to the negative x is continuous and differentiable on all real numbers, and this all real numbers, negative infinity to positive infinity, includes negative infinity. So we're good. We satisfy the criteria. Let's take the derivative of the top and the bottom. So we have the limit as x approaches negative infinity, and differentiating the top we have 2x, and differentiating the bottom we have negative e to the negative x. And let's see what happens. If I plug in negative infinity, 2 times negative infinity is negative infinity, and negative infinity plugged in here we get e to the negative infinity is e to the infinity, which is infinity, and we've got a negative in front, so that's negative infinity. No good. These two functions are continuous and differentiable on all real numbers. We've got an indeterminate form that satisfies L'Hopital's rule. Go again. So let's do this. Limit as x approaches negative infinity of 2 over negative times negative is a positive e to the negative x. And at this point, if I substitute a negative infinity for x, we get 2 over e to the negative times negative infinity is positive infinity. And so that's 2 over infinity. That's equal to 0. So always check when you're done and evaluate. And if you still get an indeterminate form, keep going, keep differentiating until you get some sort of convergent value. Or you may get something that does not exist, but in either case you'll be able to show it.